Good day, grade 11s, and welcome to another episode of the Grade 11 Geography Caps series. I want to say thank you for tuning in, and I'd like to apologize for the huge delay. My laptop got damaged, and so I had to go and fix it, and things took too long, such that I had to borrow a computer from someone else. And yeah, that's where I am at the moment. But I'd like to reassure you guys that we will complete each and every topic or subtopic hopefully before you guys write. So this means that I will be uploading a lot of videos. So I'm working really hard in the background, trying to ensure that I finish up this video, I make these videos, edit them, and upload them before you guys write. Okay, so as you can see, in today's video, we'll be continuing with the grade 11 cap series, meaning which we'll be doing the global circulation. We'll be looking at the world pressure belts. We'll be looking at major winds and the relationship between temperature, pressure, and wind, which I've actually quite demonstrated a lot in the previous videos, I think. So it shouldn't be something new to you if you watched the previous videos. So as I said, we'll be covering the global air circulation in today's video. And global air circulation, guys, is simply that transfer or that transportation of thermal energy. So let me actually write that down. Okay, so basically that transfer of this heat energy. Okay, so this heat energy can be transferred by air, right, as we will demonstrate, and also by ocean currents. Okay, so meaning which water. So this energy then is transferred or carried from the equator where there's an energy surplus. Okay, so there's more than enough energy here. There's way too much energy because the equator receives most of the insolation. So this energy is then transferred from this surplus. Okay, so surplus means more than enough. Energy surplus is then transferred to areas where there is a deficit. Okay, so that's an energy deficit. So yeah, that is what global air circulation, basically transferring the thermal energy or this energy from where there's more than enough energy to where there's energy needed. Okay, so we're trying to basically regulate the amount of energy that is distributed across the world. So hence we say that global air circulation is a response to the unequal heating of the atmosphere. Okay, we do know that the earth is heated differently. We did cover that in the last episode, and so this is a response to that. We will also cover world pressure belts, as well as the tricellular circulation, the three cells that you have to know. The relationship between air temperature, air pressure, and wind, we did cover that in the last video, but I will also reiterate it in today's video as well. We also did cover the pressure gradient force, Coriolis force, and geostrophic flow in the previous video. So please check that out, guys, if you haven't done so. And we'll also take a look at the winds related to global air circulation. So your westerlies, tropical easterlies, and polar easterlies. So that is all that we are going to cover in this video, meaning which in the next video we'll be finishing up the global air circulation with the air mass characteristics as well as the winds related to regional and local air movements. And so these two concepts will be covered in the next video, right? And let's please comment down below, what are you guys covering at the moment? Which concepts are you covering? Have you covered Africa's weather and climate? Have you covered droughts and desertification? Please let me know, guys, so that we move really quickly, okay? Right, so without wasting any time, guys, let's get into it. As I said, we did cover the relationship between air temperature, air pressure, and wind. So in a nutshell, we said that temperature differences lead to air pressure differences or atmospheric pressure differences, which result in wind. Okay, wind is moving air. Okay, and this wind moves because of a force that we call the pressure gradient force, right? Meaning which, if let's say on the left hand side there's a sunny day, and then on the right hand side it's a cold day, low insolation received on the right hand side. Okay, so I've tried to draw a cloudy day over there on the right hand side, right? So on a sunny day, we said that the sun emits its solar radiation. Okay, solar radiation, that is your solar energy or the sun energy. Okay, energy from the sun. Okay, so it emits this solar radiation towards the earth. Okay, the earth absorbs this solar radiation, so it get absorbed and then it is converted into heat energy, right? So there we go. So now the surface is hot or it is warm, right? And now the surface then transfers this heat to the air particles that are close by. Okay, the air particles or the air that is right on the surface or at the surface or close to the surface, right? So that air now receives this heat energy and gets excited, right? It receives that, converts it into kinetic energy, and so now that is movement energy. So it gets excited and it does what? And it expands. It expands, okay? And because it is expanding, the particles become far away from each other. Okay, the distance between that one and that one is huge, right? So whenever you have an air parcel that expands, we then say that it is less dense. The stuff that it is made up of is far from each other. It is not compact. Okay, the stuff that it is made up of, which is your air particles. Okay, this makes it to become less dense. Okay, so it becomes less dense, and then because it is less dense, it then rises up. It rises up because, well, the surroundings, you have cold air in the surroundings, and because you have cold air in the surroundings, it is relatively less dense than the cold air, and so it then is forced to rise up. So it is less dense, it rises up. So this is critical, right? So it rises up, and so how much force is it placing on the surface? How much force or how much pressure is it putting on the surface? Okay, so we then say that it puts less pressure on the surface. It is rising up, it is less dense, it is not heavy, it is light. And so we say that it puts a little amount of pressure on the surface. That is how an area of low pressure is formed, guys. Okay, that's how we form an area of low pressure on the surface. And by the way, we said that when you have rising air, the rising air takes its energy and travels or carries its energy to the higher altitudes. So we said that that is convection. Okay, so convection is basically that vertical movement or that warm air rising up. That is convection. So that's how that happens, guys. So this is now a relationship between air temperature and pressure. Okay, the air temperature is high because this is a warm MS, right? So meaning which its temperature is high. And because its temperature is high, that means its energy is high. And so it then rises up and puts a little amount of pressure on the ground. And so that's why we say warm air is associated with low pressure. Okay, so that's the relationship there. Now I'm gonna erase all of this and basically draw it in a much more simpler way, right? So I'm gonna have my surface over there. Let me actually place it here. So over here we have warm air rising up. And we said that we have an area of low pressure that is created over there on the surface, on the ground, right? We know that air will always move from an area of high pressure to an area of low pressure. Right, so that is a very important principle in geography. And the force that makes air to move from an area of high pressure to an area of low pressure is the pressure gradient force, right? So now you have warm air rising up. Okay, it rises up because it is less dense, guys, right? Now this means that right over here, there is a void, okay? Someone needs to fill this up, okay, because the air that was here has now risen up. And so now you're going to have air particles from relatively higher pressures moving towards this low pressure. They move towards this low pressure. They are pushed or driven by the pressure gradient force. They are coming from higher pressures, relatively areas of higher pressure than this low pressure. They will move towards that low pressure and they will do what? They will converge. They meet up there, okay? So we see convergence, surface convergence whenever we have a low pressure. So they converge, they meet up, or they collide right over there at the lowest pressure. And when they collide, there's nowhere else to go. You cannot collide and move towards the ground and move through the ground. You collide and move upwards, collide and move upwards, collide and move upwards, and you leave a void. And more air is invited to go towards this low pressure and collide with another MS, move upwards, collide, move upwards, so on and so on. That's what we see there. Collide and move upwards. Okay. So we see convergence at the surface. Okay. We call that surface convergence. So now when the warm air rises, it cools down. So it becomes cooler and cooler, it becomes colder. And if it is moist, if it has enough water vapor, it will form clouds. It will condense. Okay, but if it is a warm, dry air, it will not condense. Okay, in order for you to form clouds which are made up of water, your air has to be made up of water vapor. And so if the water vapor is not enough, then you cannot form any clouds. So now it rises up, and then at upper atmosphere it becomes cool. Okay, so I'm changing these to the blue, I guess, blue arrows. So it changed the color to indicate that temperature has now dropped. So in the upper atmosphere now, what happens is that this now cool air separates. Okay, it then separates and it moves to different directions. Okay, so we see separation there at the top. Okay, and we call that divergence. I think you guys did cover all of this, but I just wanted to make sure that everyone is on the same boat. So we see divergence. We call this upper divergence because it happens in the upper atmosphere. Okay, upper divergence. They separate these MSs, and then at some point, after losing energy, they will sink down. Okay, they will descend. Descend is a term we use for sinking down. So that cold air descends down. Okay, it sinks down towards the surface and hence puts a lot of pressure on the ground because it is heavy. Remember, cold air is heavy. It is more dense. Okay, so as it sinks down, the particles become closer and closer to each other. Okay, and they put a lot of pressure on the ground. Okay, put a lot of pressure on the ground. So an area of high pressure is then formed. Okay, so that's what happens even on a cold day, guys. On a cold day, you have cold air, of course. Cold air tends to sink down because it is heavy, it is dense. Its particles are close to each other. Okay, that's what we mean by dense, and it puts a lot of force on the ground, and hence we say that an area of high pressure is created. So it creates an area of high pressure because you have cold air. So cold air that is heavy, it is dense, and because it is heavy and dense, it tends to descend or tends to sink down and put a lot of pressure on the ground. And so an area of high pressure is then formed on the surface. But now, as these MSs move towards the surface, they cannot go through the surface. Okay, they do not go through the surface like that, and they do not have a choice, but rather move away from each other. This guy moves to the right, that guy moves to the left, so on and so on, right? So it's that continuous separation at the surface. So we call that divergence. Remember, separating is divergence or diverging, but in this case, it occurs on the surface. Remember, in that low pressure and that low pressure system, it occurred in the upper atmosphere. So we say we have surface divergence. So it diverges, moves to different areas. Okay, it seeks actually for areas of low pressure because it's coming from an area where it is compact. There's a lot of particles. There are a lot of particles like next to each other, and so it wants to move to an area where there's less particles, and so it looks for low pressure system. So basically these are all connected, and the reason why it moves, guys, from high pressure to low pressure is the pressure gradient force, right? So it is moving, and this is air that is moving is wind. Okay, so that's how wind occurs, guys. It is basically moving air that is driven or pushed by pressure gradient force. Okay, So now, if you can take a look at these guys, these are all connected. Because if I could draw this once again right over here, just gonna have a surface over there. So if we have an area of low pressure over there, and let's say an area of high pressure over there, area of high pressure over there. Okay, the area of low pressure was formed because of warm air rising up. Okay. Warm air is not formed by an area of low pressure, but rather an area of low pressure is formed by rising warm air. So the warm air rises, right, and leaves a void over there. And then now air coming from this area of high pressure will move towards that low pressure over there, pushed by pressure gradient force. So colder air moves to this warmer region. It arrives here, becomes moist, and then it becomes unstable. By unstable, it basically means it rises up. Okay, just to make things simple, that's what we mean. By stable, it descends, air is descending. So it converges over there, rises up, it then diverges, it becomes cool, right? It diverges in the upper atmosphere, and then it loses energy at some point, and then it descends and forms an area of high pressure. And on that other side, that's what we see as well. Descends and forms an area of high pressure on this side as well. Okay. Now you can see that you have a continuous circulation of air. Air is circulating like that, right? So this is then called a cell. These are cells, guys. Okay, and we'll talk about cells. We have three major cells that operate on a world on a large scale. That is what a cell is, that continuous rotation or circulation of air, so on and so on and so on. This is a relationship between a low pressure system. Low pressure system we call a cyclone, and then and a high pressure system which we call an anticyclone. So there is a relationship over there, guys. So this is important to note, right? Okay, I wanted to point that out. If you have temperature differences, this will cause pressure differences because, well, it was cold over there, and so it formed an area of high pressure. It was warm over there, and we formed an area of low pressure. And because there's a relationship between high pressure and low pressure, where air always moves from an area of high pressure to an area of low pressure, these are connected, very much connected, such that they form what we call a cell. Now, let's take a look at the two ways to form an area of low pressure before we actually begin the lesson. Okay, so there's two ways to form an area of low pressure. We've already covered the first one, which is by insolation, or basically initiated by high air temperature. If an area receives a lot of insolation, high amounts of insolation, okay, exposed to a lot of the sun's energy. So the sun transfers this solar radiation towards the Earth's surface, and the Earth's surface becomes warm, and then it sends or transfers this heat energy to the air particles that are directly above it, and then these air particles rise up, right? So they become they receive a lot of energy, they become excited, they rise up, they become less dense, and because they do not apply any force on the ground, we say that an area of low pressure is then created because, well, you have warm air that is less dense having to rise up because of insolation, because they have enough energy to do so, because they are less dense. So that's the first way. And then the second way is by upliftment. Okay, some would argue that these are quite the same, but they are quite different, to be honest. So the upliftment now occurs when you have cold air. Sorry about that. So when you have cold air meeting up with warm air, right? So you have cold air on the right, which is dense, which is heavy, and it meets up with warm air on the left, which is less dense. What's going to happen there? They cannot go through each other like that. And so what happens is that cold air wedges underneath. Okay. So it moves underneath the warm air, forcing the warm air to rise up. So the warm air rises on top of the cold air. Okay, you should imagine something like this. So let's say this is the cold MS, and so the cold air is moving towards the warm air, the warm air is then forced to rise up because it is less dense. Okay, and then we say that the cold air wedges underneath. Okay, they also say that it forms a wedge, and the warm air is then pushed upwards. It is uplifted, pushed upwards because it is less dense. Okay, and so if it is pushed upwards, so this is by force, right? And so now, if it is going to be pushed upwards, how much pressure is it placing right over here on the ground? How much pressure is it placing over here? So it is low pressure, right? So an area of low pressure is then formed on this side right over here. Okay, so that's the second way you form an area of low pressure. First, by insolation. Second, by upliftment. So this is critical to note, guys, especially if you want to understand how pressure belts form. So that was a pre-lesson. So now we actually get into the actual lesson. So, but this is vital for you to understand everything that we are going to cover right now. So first things first, we are going to start with the world pressure belts. What is a pressure belt? Okay, simple, guys. A pressure belt is a zone of high pressure or low atmospheric pressure. Okay, particularly on the ground. Okay, so it's a zone of high pressure or a zone of low pressure. How much pressure does the air place in this distance or in this particular region? Okay, overall, right? So that's what we are going to cover here. So that's what pressure belts really are. So we have 4 types of pressure belts, and you have to know their names, you have to know their locations, you have to know what causes them, you have to know their formation. So I'm going to start off with the unequal heating. Okay, right over here where it says illustration. Okay, we know that right at the center, our lines of latitudes say that this is 0 degrees, the equator. So that's the equator, right? And that is 90 degrees. The polar regions, that's 90 degrees. I'm actually going to erase this. Let's erase that. And this is 90 degrees south. Okay, southern hemisphere. From the previous videos, we know that due to Earth's shape, okay, due to its shape, these 2 areas, the equator and the polar regions, they receive unequal heating. They receive unequal insolation. We said that the equator receives most of the insolation, okay, because it receives direct sun rays, and these sun rays are concentrated over a small area, right? So that makes the heat to be intense. So they receive a lot of heat right over here, the equator. And then the poles receive less energy. Okay, so they receive less energy, they receive less insolation. Remember, less insolation, that's less energy. So this is energy deficit. If you remember quite well, guys, energy deficit, not enough energy. They lose more energy than gain energy here, because over here you have the high albedo snow, which reflects a lot of the little insolation that is received. And then right over here, you have an energy surplus. So the equator receives a lot of insolation. Okay, because it receives a lot of insolation, we expect a lot of warm air to rise up. Okay, so that insolation that is received throughout the year is absorbed by the ground. The ground converts that to heat energy and transfers that heat to the particles right close to the surface. The particles gain energy, absorb that energy, and convert that to kinetic energy. They now move. They now move and expand and become less dense. And hence, how much pressure are they forming on the ground? That's low pressure. Okay, low pressure on the ground, guys. So the equator as a whole, from 0 degrees to 5 degrees actually. Okay, from 0 to 5. So 0 to 5, so that's 5 degrees south, that's 5 degrees north. Okay, let me zoom in, guys, so that you can see this quite clearly. I'm going to erase that. Okay, so from 0 to 5 degrees, we see a lot of warm air rising up, hot air actually. So in this region, okay, this vast area from over there all the way to that side, around the earth, we have hot air, moist air, very moist air, that continuously rises up. Now, I'm going to demonstrate this warm air rising up. We demonstrate this on this side, guys. Okay. Okay, so this is warm air rising up. So I'm just going to use red to indicate that air is basically rising up. Guys, this is the same thing, right? This is the same thing, okay? This over here, this is the same thing as this, but it's basically just rotated, okay? This is just rotated to that side so that it points like that, okay? So that we can show everything right on this same diagram. Yeah, don't be confused by these arrows. These arrows mean that air is rising up from the surface, okay? We are demonstrating this, but on this diagram, okay? So please note that. So warm air is rising up, and we said that when warm air rises up, it will then diverge at the upper atmosphere, okay? So it will diverge, it will separate, move to different directions, okay? Move over there, move over there. So that is important to note there. Now, let's get back to our pressure belts. So we're saying that at 0 to 5 degrees, we see an area, this region. This is an area of low pressure. This is a zone of low pressure. So that means that it is a belt. It is a pressure belt. Okay. And we call that zone of low pressure. We call that the equatorial low pressure belt. The equatorial low pressure belt. I did not say low pressure belt. I did not say equatorial belt. I said the equatorial low pressure belt. So you have to ensure that you write that in full. Okay? Write it in full, guys, or else you are not going to get all the marks. So that's the name of the pressure belt. Okay? It's the equatorial low pressure belt. And this is found, as I said, this is located, that is its location between 0 and 5 degrees north or south of the equator. And this equatorial low pressure belt is formed. How is it formed? Well, hot, moist air. Okay, we have hot, moist air, and that hot, moist air exists due to intense heating, due to a lot of insolation received. So the hot, moist air rises and expands and creating an area of low pressure. Okay, the first way we discussed the way in which the low pressure forms, right? So creating an area of low atmospheric pressure on the surface. Okay, creating an area of low atmospheric pressure on the surface. So that's the first pressure belt, guys, the equatorial low pressure belt. Okay, between 0 and 5 degrees north or south of the equator. So that's what I'm going to write down in this big diagram. I'm going to write down the equatorial low pressure belt between 0 and 5 degrees. Okay, so this means that this is 5 degrees north and that's 5 degrees south, right? So in this area we see a belt forming, an equatorial low pressure belt, and I'm actually going to use red. Okay, so that's the equatorial low pressure belt over there between 0 and 5 degrees north or south of the equator. And again, as I said, guys, it is formed by that hot, moist air rising up due to the excessive amounts of insolation that is received over here in this region. Now, we know that warm air rises up, okay? So it rises up, and then at the upper atmosphere, it diverges, okay? We see that upper divergence, okay? That's exactly what happens here as well. Between 0 and 5 degrees. So I'm just going to illustrate the rising air with the arrows. So this is that hot, moist air rising up, and then in the upper atmosphere it separates. Okay, it moves to it's trying to move towards the equator. Okay, to warm up the equator. But now what happens is that as it is moving towards the equator, it loses energy on the way. Okay, it loses energy and then it sinks down. Okay, because now it is cold, right? So it then sinks down at the subtropics. Okay, at around 30 degrees. Okay, it was trying to move towards the poles. Okay, remember global air circulation. This is thermal energy moving from the equator to the poles. But because it loses a lot of energy, it then sinks down in the tropics or on the tropics. So now you have this cold air sinking down towards the ground. Okay. So what happens then? Okay, when you have cold air is dense, it is heavy, it descends, moves towards the ground and puts a lot of pressure on the ground. And so an area of high pressure is then formed at 30 degrees, guys. At 30 degrees. So this happens around 30 degrees. So this is 30 degrees north. This also occurs at 30 degrees south. Right, so this we call this region the subtropics. So now you then form an area of high pressure over there. So there's an area of high pressure at 30 degrees. Okay, an area of high pressure over there. Okay, and again, should have had low pressure there between 0 and 5, and high pressure over there at 30 due to that cold, dense air. Okay, so we see an area of high pressure at 30 degrees and an area of low pressure at 0 to 5 degrees. Okay, now this area or this zone of high pressure at 30 degrees has a name. Okay, it's a pressure belt. So a pressure belt is formed there. That's a zone of high pressure. Okay, so we could then call that the subtropical high pressure belt. The subtropical high pressure belt. I did not say subtropical pressure belt. I said the subtropical high pressure belt. Okay, and it is formed around 30 degrees north or south of the equator. And the way it forms is that the equatorial warm moist air loses energy at about this region when it is approaching the poles, and then it becomes cold. Because when you lose energy, that means the temperature also decreases because, well, temperature measures energy. Okay, temperature is energy actually. So energy of the particles. So it becomes cold and sinks down, creating an area of high pressure on the surface. So that is the subtropical high pressure belt. Okay, at 30 degrees, guys, north or south of the equator. Right, so we have that subtropical high pressure belt at 30 degrees. Okay, I hope you can see that, guys. I'm really trying to ensure that I write it right on the line. So that's what we have over there. So again, the name is important, the location, as well as the formation. Right, so that's what we see there, an area of high pressure that is formed over there. I'm missing some, should have completed these arrows over there. So now, as you can see, guys, on the surface, what happens? Okay, on the surface, these diverge. Okay, this moves to that direction, that one over there, and then the other one moves in the opposite direction. We see surface divergence when we have a high pressure on the surface, right? So that's what we see over there. So this is going to be important when it comes to your winds, your major winds. Okay, as well as here we see divergence. Air separates, moves to different directions. There we go. Okay. We'll talk about this concept called adiabatic warming. Let me actually just touch on it a bit. So what happens, guys, is that you have when you have cold air sinking down, right? When cold air sinks down, it tends to warm up. So it becomes warm and warm and warm, such that when it arrives or when it reaches the ground, it has warmed up. Okay, we say that it warms up due to adiabatic warming. As it rises up, it cools down. Okay, as it sinks down or descends down, it warms up. So we call that adiabatic warming. So the sunny weather that we experience at around 30 degrees is due to this. So we'll touch on this more and more in the coming topics. Right, so now you have air that is moving towards, so you have this warm air rather, okay, this is a warm air, okay, because now when it reaches the ground, it is already warm, then it separates to different directions. So this is a warm air right over here. And this warm air approaches or is approached or meets up basically with a cold air. Okay, it meets up with cold air from 90 degrees and they meet up at around 60. This is 60 degrees south in this case. So they meet up at 60 degrees south. So we know that warm air, Okay, we'll talk about which air is that. So warm air and cold air meet up at 60 degrees. Okay, and we said that whenever you have warm air and cold air meeting up, we see upliftment, right? So now this warm air is definitely going to be lifted upwards. It's going to be lifted upwards, the warm air. It will rise up. It is lifted upwards by that cold air, okay, that comes from 90 degrees, okay, moving towards the 60 degrees, right? And so, therefore, an area of low pressure is then formed because of this upliftment here at around 60 degrees. So, we see an area of low pressure forming by upliftment over there, 60 degrees. So, we see an area of low pressure forming at 60 degrees. So that is a zone of low pressure over there at 60 degrees. Okay, so I'm going to have L over there. So this represents low pressure, 60 degrees. So meaning which at 60 degrees we have another zone, but this zone is now the zone of low pressure, 60 degrees north. And by the way, at 60 degrees, we also have another term for that. So 60 degrees is also called the polar front. Okay, polar front. It's where the cold air and warm air meet up. Okay, that boundary between them is the front. But because it is near the poles, we call it the polar front. Now, this zone of low pressure then has a name. It is a belt. Okay, so that's a zone of low pressure, and it is called the subpolar. The subpolar low pressure belt. Okay, subpolar low pressure belt. It occurs at 60 degrees north or south of the equator. And it is formed by upliftment, guys, as I said. So warm subtropical westerlies, we'll talk about these. That is the warm air. Okay, that is that warm air. We call it the warm subtropical westerlies. They meet up with cold polar easterlies. Okay, so these are major winds. We'll talk about these, as I said. They meet here at the polar front. And then what happens? The warm air then gets pushed up by the cold air, creating an area of low pressure over there. Okay, so formation of low pressure by upliftment. Okay, so that's how the subpolar low pressure belt is formed. You have to have warm air meeting up with that cold air over there at 60 degrees. Right, so there you go. That's the subpolar low pressure belt. It has formed at 60 degrees. So now let's complete all of these circulations. So of course we know that the warm air rises up and then it does what? It separates. Okay, moves to different directions. So becomes cold. Yes, it cools down, becomes cold and separate. There we go. So it separates. There we go. Okay, so that's what we see over there. And yes, the low pressure. Okay, this warm air, this is supposed to be warm, right? So we're supposed to have a red arrow over there, and we're supposed to have a red arrow over here. Okay, so this air right over here is relatively colder than the air that is at the equator. Okay, so the air that moves towards the equator like this, moving towards the equator, is relatively colder. Yes, it is warm air, but at the equator we have hot air. Okay, so towards the equator, I'm just going to make them, the color is going to be, I'm going to pick a yellow color. Okay, they are relatively colder. Okay, not red hot. Okay, like as you see over there. Okay, so it's temperature is relative, guys. You're cold, colder than what? Colder than which MS? So we're saying that right at 60 degrees, we know that this warm air meets up with the cold air. Okay, so it meets up with cold air coming from the 90 degrees and it is pushed upwards. So it rises up and that's how we get that area of low pressure over there, the subpolar low pressure belt. And then as it sinks and then as it rises up, it cools down and diverges. Okay, moves to opposite directions. Okay, and then at 90 degrees, okay, 90 degrees loses energy and then it sinks down. Okay, so at 90 degrees, anyway, it's already cold over there. Okay, remember these are the poles, so we're already expecting a high pressure belt over there. Okay, so at 90 degrees, because it is cold, there's low insolation due to oblique insolation, due to high albedo snow, a lot of energy is reflected back. So it's already cold over here. So of course, if you have cold air, the cold air tends to sink down. Okay, so we already have a area of high pressure over there at 90 degrees. Should be an area of high pressure over there. Okay, so at 90 degrees, we have this area of high pressure due to low amount of insolation received, low energy received. We've been saying that again and again and again and again. The poles do not get enough energy. So it's already cold over there, and so it's an area of high pressure. This area of high pressure, we then call it what? We call it the polar high pressure belt. The polar high pressure belt. It's at 90 degrees. You have cold, dry air here that exists due to oblique rays, high albedo snow, so on and so on. So this cold, dry air descends, creating an area of high pressure on the ground. Okay, so that's really simple, similar to the equator, because the equator is warm, and because it is warm, you have hot, moist air rising up, and so forming an area of high pressure, of low pressure there. Okay, so we have a polar high pressure belt at 90 degrees. Okay, so there you go. All of those are your pressure belts, guys. You have to know their locations. You have to know their names. Okay, be able to name them, be able to identify them when you are given a diagram, and also be able to describe or explain their formation. Okay, so that is very important. Now, looking at these over here, this circulation, guys, we definitely notice something. Okay, this air rises up, it then separates at upper atmosphere, and then it loses energy at some point, and then it becomes cold, and then it sinks down, and then it warms up by adiabatic warming, and then it separates on the ground, and then so on and so on. So you can see we have a circulation over there. And if you look at this clearly, we have 1, 2, 3 circulations. Okay. And we called circulations of air, we call them cells, right? So these cells have names, and you have to know their names. It's very important that you do so. So you have the Hadley cell, which is number 1, the Hadley cell, and then number 2 is the Ferrel cell, and then number 3 is your polar cell. Okay, they have names. So this over here, it exists between 0 and 30, so that is the Hadley cell. And then between 30 and 60, that is the Ferrel cell. Between 60 and 90, that's the polar cell. And that's, yeah, we replicate this again. Hadley cell between 0 and 30, Ferrel cell between 30 and 60. I really hope my spelling is correct. So these are the 3 cells you have to know. Their locations, their names, of course, and also how they form. So describing how they form is really simple. So for an example, if I were to describe the formation of the Hadley cell is formed by this. So hot, moist air in the equator rises up, expands, and it becomes less dense and creates an area of low pressure there, and then separates or diverges at upper atmosphere. Okay, and then while moving towards the poles, it then loses energy, right? Okay, so I'm basically drawing the person who's going to mark me, I'm drawing them this circulation. You have this hot, moist air rising up here at 0. It then separates, it diverges at upper atmosphere, moves towards the poles, but then it loses energy at 30 degrees. It then sinks down, right, and creates an area of high pressure, and then separates, okay, diverges at the surface at 30 degrees and moves towards the equator. That is me that is me explaining basically how the Hadley cell has formed. Explain it by using these arrows over there. Okay, right, so you have to paint the picture there. Right, so this is what we have now. We have areas of high pressure, we have areas of low pressure. Okay, meaning which we have pressure differences. When we have pressure differences, what tends to occur? Wind tends to occur. Air starts to move from an area of high pressure to an area of low pressure. Okay, because now we have pressure difference is. The pressure gradient force will start to act now, okay? Drive air to move from an area of high pressure to areas of low pressure, okay? This then results in our major winds, right? So now at 30 degrees, you're going to note that we have an area of high pressure over here, okay, at 30 degrees at the subtropics. And I'm sure you and I both agree that air will move from an area of high pressure to an area of low pressure. So air will move from 30 degrees towards 0 degrees, okay, towards 0 degrees. So air will move like that. And even on the northern hemisphere, that's what we expect, air to move like that, okay, from an area of high pressure to this area of low pressure, which is the equatorial low pressure belt. And the reason why it moves is due to the pressure gradient force. Pressure gradient force forces air, drives air to move from an area of high pressure to an area of low pressure. And so we expect something like this, but that is not correct. We have the Coriolis force. So if I were to demonstrate over here, okay, so if this is my area of high pressure, so if there was no Coriolis force, air would move straight in a straight line like that towards the low pressure. But because now Coriolis force occurs, okay, Coriolis force exists due to the rotation of the Earth, air is then pushed to the left in the southern hemisphere, okay? It is pushed to its left in the southern hemisphere and pushed to its right in the northern hemisphere, okay? So instead of air moving like that, air is then deflected to move like that, okay? So now air, yes, is moving towards the low pressure, but it moves like that, moves like that. So now as you can see, guys, it is coming from which side? It is coming from the southeast, okay? So we then say that this air, or this moving air, this wind, is the southeasterly wind, okay? But now because it occurs in the tropics, okay, the tropics, which are these areas over there, so we then say these are your tropical easterlies, or this tropical southeasterlies, okay? So that's what we see. It is deflected to its left in the southern hemisphere, okay? So that's what we see over here. We see tropical southeasterlies. They move from the southeast, driven by both the pressure gradient force and Coriolis force. Okay, the Coriolis force is responsible for the deflection of this air, and then the pressure gradient force is, of course, responsible for the movement from high pressure to low pressure. And then what about in the northern hemisphere? In the northern hemisphere, air is deflected to its right. So instead of moving in a straight line like that, it's going to move to its right. Okay, you should basically just imagine yourself as this air, or as this wind moving towards, moving down like that. Okay, with your face pointing that direction. So your right would be this, meaning which in the northern hemisphere, then air should look something like this. Okay, this major wind to its right. This is its right. Then what is its wind direction? What is this wind direction? This is from the northeast. Okay, so these are your tropical northeasterlies because they exist in the tropical regions. And then this is your tropical southeasterlies. So all in all, collectively, basically, the winds that blow from 0 to 30 degrees, we call them easterlies, okay, because they all come from the eastern side, okay. We call them tropical easterlies, right? So those are your tropical easterlies, and there we go. So these are the tropical easterlies, and they exist between 0 or blow between 0 and 30 degrees north or south of the equator. They move from the subtropical high pressure to the equatorial low pressure, pushed by the pressure gradient force. And then they are deflected by the Coriolis force, and they become tropical northeasterlies in the northern hemisphere and become tropical southeasterlies in the southern hemisphere, right? Hope you guys are with me there. Okay. So these winds, major winds, they bring cooler air, okay, relatively cooler, okay, to the equator. Remember, the equator has hot air, okay. So they bring cooler air, but when they approach the equator, they become moist and they become unstable, and then they form rainfall. So there's a lot of rain there at the equator, okay, because of they converge there, okay. So they converge at 0 degrees. That's why we call this point at 0 degrees, we call it the ITCZ. This is the point of convergence. This ITCZ means intertropical convergence zone. That is the ITCZ, guys. Okay, it does shift depending on the season. It can go up, it can go down. It's an imaginary line. Okay, but we'll talk more about this in grade 12. So that is the ITCZ. Okay, the intertropical convergence zone. This is where tropical easterlies converge. This is where they meet. Okay, they meet up, they rise up, they form rainfall, they diverge in the upper atmosphere, so on and so on and so on. Okay, the ITCZ. Right, and then now we're saying that this cold air that is sinking right over here then becomes warmer and warmer, and then it separates. Okay, diverges. This moves to that other side, and then this moves to that other side, and there's an area of high pressure that is formed there. So while this air mass is moving that side, you also have an air mass that moves this side, meaning which now you also have air that moves from this high pressure to this low pressure over here, because you have a high pressure there, then you have a low pressure there. Okay, so but then it should be deflected, guys. Remember, there's Coriolis force there. Okay, and then this is the southern hemisphere, so it should be deflected to its left, meaning which its left should be this. This is its left. So that's what we should see there. Air or moving air that is moving this direction. Okay, moving something like this. There we go. Okay, let me erase that. Moves towards the low pressure, but it is deflected to its left, and hence it moves in this direction. But then what is this wind direction? It is from the northwest. Okay, so this is a northwesterly direction. So we then say that these are northwesterlies. Okay, northwesterlies. And then that's what we see over here as well. But now these are deflected to their right. So instead of moving straight like this, they move like that. Deflected to their right. This is the northern hemisphere, remember? So this is what we see over there. Moving air or major wind that is moving in which direction? Or moving from which direction? That's how we report wind direction. So it is coming from the southwest. So we then call these southwesterlies. So all in all, both of them are westerlies. Okay, so that and that, those are your westerlies. Okay, but because they are from the subtropics, we call them the subtropical westerlies collectively. And they blow from 30 degrees to 60 degrees, right? We call them subtropical westerlies, blow from 30 to 60 degrees. So they move from subtropical high pressure to the subpolar low pressure at 60 degrees. And they bring this warm air towards these cold areas, okay? They are deflected by the Coriolis force, and then they become northwesterlies in the northern hemisphere and become southwesterlies in the southern hemisphere. Right, as I demonstrated, guys, when westerlies meet with cold polar easterlies, they are forced to rise up, cool down, and form rainfall. Okay, and this process of this upliftment basically also leads to what a special system that we call a mid-latitude cyclone. Okay, we'll talk about these, cover all of this in grade 12. So it leads to a system of low pressure. That's what a cyclone is, which we call a mid-latitude cyclone. This upliftment of warm air by the cold air. Okay, so these are the subtropical westerlies, guys. Yeah, I should have used the same color over there. Right, so yeah, so that's your southwesterlies in the northern hemisphere and northwesterlies in the southern hemisphere, but we collectively call them the subtropical westerlies. And now, between the polar high pressure belt and the subpolar low pressure belt, we're expecting to see air moving from this high pressure to that low pressure, right? Because there's a high pressure there, there's a low pressure there, and air always moves from an area of high pressure to an area of low pressure. And now, because we're in the southern hemisphere, this should be deflected to its left. Okay. So instead of moving straight like that, it's going to move like that. Okay. So that's what we are going to see there. So between 60 and 90 degrees, we see this this major wind over here blowing from the polar high pressure belt to the subpolar low pressure belt. And then in the northern hemisphere should be deflected to its right. It could move like this, but due to Coriolis force, it is deflected to its right. So its right is this, right? So that's what we should see there as well. So we should see something like this. So what do we then call these? They are coming from what direction? They are coming from the northeast, okay? So these are polar easterlies, or they are polar northeasterlies, okay? So these are northeasterlies. Zoom in, okay? Polar northeasterlies. And then on the southern hemisphere, we have polar southeasterlies. Polar southeasterlies in the southern hemisphere, okay? But collectively, what do we call them? Okay, all of them are easterlies, right? So we have polar easterlies there collectively between 60 and 90 degrees. So these are found between 60 and 90 degrees, as we said, right? And they move from the polar high pressure to the subpolar low pressure. And yes, these winds, these cold winds, remember they are coming from the high pressure, the polar high pressure from the poles, so they are cold. These cold polar easterlies, they force the westerlies to rise up when they meet up at the polar front at 60 degrees, as I did cover, as I did mention. And then they are deflected by the Coriolis force and become polar northeasterlies in the no, this should be polar southeasterlies, right? Yeah, polar southeasterlies in the southern hemisphere and polar northeasterlies. Polar northeasterlies, yes, in the northern hemisphere. Right, so that's everything, guys. I hope that was beneficial to you. I really hope I did make it simple for you. I know there's a lot of illustrations here, but this is all for you. I'm trying to ensure that I make it as simple as I can on my side. I really hope that you do get it on your side. So again, thank you guys. I really, again, apologize for the late delay. I am really sorry. And from now on, I promise to ensure that I upload frequently. Okay, so thank you for tuning in. Please, let's continue to subscribe. Let's continue to share. Let's continue to comment and like and grow this channel more so that it can help a lot more students. Okay, see you in the next one.